After the time of Archimedes, mathematics is going to flourish. And it's going to flourish all the way through what's known as the Hellenistic Age. And one of the mathematicians along this timeline is by the name of Eratosthenes. Eratosthenes is known as Beta. And when you read your book, you will understand why people refer to him as Beta. But Beta, man, I would love to study at his feet. And one of the things he does is he figures out a way of figuring out prime numbers. And it's known to this day by his name. And it's called the Sieve of Eratosthenes. And the Sieve of Eratosthenes is a very elegant way of determining primes. Unfortunately, it does not have predictability, meaning it's brute force. To determine if the number 9,731 is prime, you just got to work your way up to it. So it's not like you can just throw a number into the sieve and say, hey, spit the answer out. But it does give us a methodology for figuring out primes as far as we want to go. And with the advent of computers, we now have the ability to go a very long way. Let's take a look at how the sieve works. And to do that, I'm going to have to change the mode in which this presentation takes place. But I think you'll get something out of it. Greetings, the Sieve of Eratosthenes. Well, first off, we need to begin with what was Eratosthenes up to. Well, he was trying to figure out a methodology for determining what numbers are prime. And it's important to remember, what is a prime number? A prime number is a number that can only be divided by one in itself evenly. So, beginning with this idea, we're going to begin with this concept of how do we go about finding prime numbers. And Eratosthenes said, basically, we've got to list out all of the numbers. And by listing them, and I'm going to list them in basically our base 10 format, we're going to begin to understand what Eratosthenes is all about here. Now, for Greek mathematics, 1 was actually a problem. 1 is such a special number because 1 times itself, no matter how many times, remains itself. It is unity. And for that very reason, it gets a special place in all of mathematics. For the Greeks, it was basically a number they wanted to try to avoid in some cases, and in this debate being one of the cases. So 1 is said to be neither prime nor composite. It is a special one of our counting numbers. And it is the only counting number that is neither prime nor composite. So Eratosthenes said, look at all of the numbers we have and find the smallest number that's in this list. And this list to Eratosthenes is the sieve. And he says, all right, 1 has a special place. Find the smallest value in the sieve. It must be prime, because there's no number smaller than 2 that was able to divide into 2. So 2 must be prime. Then Eratosthenes said, well, if 2 is prime, let's start multiplying by 2. We know that 2 times 2 is 4, and therefore 4 cannot be a prime number. It basically falls out of the sieve. And then Eratosthenes went on to say 2 times 3 is 6, so 6 must also fall out of the sieve. It cannot remain. And then Eratosthenes said, keep doing this using the only prime number we know is 2, and we get this big set of numbers that all fall through the sieve. And they're all identified in green here. All of those numbers we know cannot be prime because we've demonstrated their composite by showing that 2 divides into them, which is a number other than 1 in themselves. And once Eratosthenes did this, he said, let's go back and look at the sieve. And he said the green numbers are out of the sieve, and so we're going to look at what numbers are left. And so he said, all right, let's now look at the smallest number left in the sieve, which is 3. The dark blue numbers are out, they've fallen out. And basically Eratosthenes says to himself, start multiplying by 3. And 3 times 2 is 6, and 3 times 3 is 9, and then 3 times just about any number you want, and there they are.
all of these green numbers would have to fall out of the sieve because we know they are multiples of 3. Now, some of these numbers we know have already left the sieve because they were multiples of 2. So the dark blue numbers were the multiples of 2. Boom, they're gone. But now you can see the green numbers are the multiples of 3 that had been left in the sieve, and we know they drop out. Now notice, what's the smallest number that 3 basically forces out of the sieve on its own, and that number is 9, the first number in green. So remember, 2 forced 4 out, 3 forces 9 out. And we're going to do the same thing one more time. We're going to look at our sieve. We're going to update it so all of the dark blue numbers are gone. The numbers in white are still in the sieve, and we want to find the smallest value that's still in the sieve, which we can see is 5. And since no number smaller than 5 divided into 5, it's safe to say 5 must be a prime number. And we're going to begin multiplying all of the multiples of 5, and we get 5 times 2, 5 times 3, 5 times any number you really need, and we get these two nice columns for the multiples of 5. But again, some of these numbers have already been removed either by being multiples of 2 or being multiples of 3. So what we do is we look at, well, what got forced out by 5, and it's just the green numbers. And we see the number 25 is the smallest number removed by 5. Now let's recap. 2 forced out 4. 3 forces out 9. 5 forces out 25. I think I'm starting to see a pattern with what a prime number forces out as its smallest composite number. Well, let's update our sieve, and we know that the next number in the sieve is 7, has not been forced out by 2, 3, or 5, so no number smaller than 7 divided divided 7 or had a 7 as a multiple, so 7 must be a prime number. Let's go look at the multiples of 7. And there they are. They're in green. But some of these numbers in green have been forced out by either 2, 3, or 5. What's the first number of all of these green numbers that 7's going to force out of the sieve? Well, let's take a look. And there it is. It's 49. And the reason for this, if you think about it, is what are the prime factors of 49? 7 times 7. What are the prime factors of 25? 5 times 5. The prime factors of 9, 3 times 3. The prime factors of 4, 2 times 2. So notice if 7 can only get to 49 first, tell me about all of the white numbers, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47. Predict what do you think those numbers are going to be? Are they going to be composite somehow? Are we going to find a prime number larger than 7 that somehow backtracks and gets these numbers less than 49? And the answer is no. Those numbers we know are prime. So we look at the list, we update it. 11 is the next prime. What's the first number that 11 is going to remove from the list? I think if the pattern holds, it will be 11 times 11, which is 121. So here are the multiples of 11. And when I superimpose the dark blue, the numbers that have already left the list, we see 121 is, in fact, the first number that 11 removes from the list. And in this way, we see the fact that, okay, all of the numbers that are still in the sieve, the numbers in white that are less than 121 must be prime. So that means I know for a fact 2, 3, 5, 7, and 11 are prime because we've built up to them, but I can also kind of look ahead and go, okay, if I have updated my sieve correctly, 11 squared is 121, I know every number that has not been removed from the sieve up to 121 must now be prime. This means we move on to 13. 13 times 13 is 169, and when we superimpose, boom, here it is. There are no prime numbers that are going to divide 167 or 163 or 127 because 13 doesn't get to a new number in the sieve until 169. So Eratosthenes, in doing this problem, was really able to figure out, hey, this is how we can determine if numbers are prime, but he's also building very rapidly a list of prime numbers for us. And that was the power of the sieve of Eratosthenes. And then here's the updated list where you can see 1 is red, it's neither prime nor composite. Everything in light blue is a prime number. Everything in the darker shade of blue is a number that is composite and is basically then divisible by a prime number. And this is what the sieve of Eratosthenes was able to do for us. Now, how can we use this in practical terms? Well, is the number 923 a prime number? Well, I don't know. Let's take a look. We know that any composite number can be expressed as a product of primes, so now we just need to check to see what are all of the primes less than 923. Well, do we really need to check all of them? We know 2 pushed 4 out of the sieve. We know 3 pushed 9 out. 5 pushed 25. 7 pushed 49, etc. So let's jump up our list of primes for a minute. 29 is a prime number. 29 times 29 is 841. The next prime number is 31. 31 times 31 is 961, which is more than 923. So if 923 is going to be a composite number, it must be divisible by a prime number less than 31. So all we need to do is check the primes less than 31, 2 to 31. And if we do this, that means we only need to check 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. And if we gun through this list and we check these with respect to 923, 2 does not work, 3 does not work, 5 does not work, 7 leaves a remainder of 6, 11 gives us a remainder of 10, 13, a remainder of 0. So what does this mean? It means that 13 times 71 is 923, and therefore 923 is not prime, but has 2 prime factors, 13 and 71. And this is how you use the sieve of Eratosthenes. And I hope this helps.
Now, since you've seen how the sieve of Eratosthenes works, and you've seen some examples, I hope this helps you understand the brilliance of the sieve of Eratosthenes. Quite simple, but also quite powerful. I hope this helps.